Okay, welcome everyone. Thank you for coming. This is the final lecture of our second week of the MTV Nuclear Engineering Summer School, and I'm pleased to introduce today's speaker, Professor Paul Sellin from Surrey University, where he is a professor of physics, doing research that includes radiation detectors. And today he's going to talk to us about one particular kind of detector called perovskite-based detectors. So Paul, I'll pass the floor to you and just mention quickly, as usual, please put questions in the chat. I'll monitor the chat and we'll take questions at the end. So Paul, please go ahead.
Great, thanks, Sean. Thank you so much. So welcome everyone. It's my pleasure to speak to you today as part of your MTV Nuclear Engineering Summer School. So greetings from London. I'm at a university, Surrey, which is just outside London in the UK. And I'm going to give you an overview about this unusual class of radiation detectors, which are called perovskite materials, made from perovskite materials. Now, again, there's a lot of you online today. You'll have come from a range of backgrounds, I'm sure, so perhaps you're very familiar with radiation detectors already. Perhaps this is a new area for you. Needless to say, traditionally, radiation detectors have been fabricated from a range of semiconductors such as silicon and germanium, or from scintillating materials. There's some very common inorganic scintillators such as sodium iodide, cesium iodide. But in the last 5 years, we've seen this new family of detector materials come along as quite a disruptive technology based on these unusual materials called perovskites. So if, like me, your chemistry is limited, which is certainly my situation, I had to learn a few new acronyms to work with these materials. So you can see on my opening slide there's a picture of 5 crystals, which are all perovskite crystals. They're all lead halides. So you can see most of them have got lead in the formula. They've all got a halide. They've got, in this case, chlorine, bromine, or iodine. And then they've got an organic molecule, which is abbreviated, in this case, to either Ma or Fa. And Ma stands for methyl ammonium and Fa stands for formamidinium. And so you might need to brush up your organic chemistry to check out what the full structure of those molecules are. And FAMAC is actually a shorthand for a bit of everything. So it's Fa and Ma blended together. And the immediate thing you may think when you look at those, obviously there's a color change. So it's telling us that the optical band gap is varying across these materials. If we have a crystal that's almost transparent, its band gap is at very high energy, short wavelength, and all optical light's going right through. If we've got crystals which look black, so this is the same as a silicon wafer, then it's because the band gap is quite short, long wavelength, and all the optical light is absorbed. And there's some lead bromide, such as Ma lead bromide in the middle, which are nicely colored. So that sets the scene. Let's just go through, well, let's see where we're heading this afternoon. So I'm going to talk to you, again, to give an introduction to perovskite detectors. I'm going to tell you about how perovskite materials are grown, crystal growth. We're going to look at some of the key charge transport and electrical properties. We're going to, of course, talk about gamma spectroscopy, because that's a key area that a lot of people are interested in. And then we're going to look at X-ray imaging, which is another application area that's very interesting for perovskites. And last but not least, we're going to talk about how perovskites can operate in a dual mode. And these materials also have good scintillation properties. And so this is makes it a fascinating material system, because we can either go for a charge-based detector or a scintillating-based detector. So let's introduce them in a bit more detail. So I've said already about the fact that they contain unusual organic molecule. So you can see from this slide that perovskites cover a wide range of materials and applications. And they've come up through the solar cell and photonic community. So 10 years ago, perovskite materials were first introduced. They were of great interest for photovoltaics, for solar cells. And they've now increasingly crossed over into radiation detection. So let's look here at an Ma lead halide. So CH3, NH3, lead, and then the halide ion, which could be iodine, bromine, or chloride. So the structure is unusual. It's a methyl ammonium organic cation shown in this picture sitting in the middle, surrounded by a lead halide octahedra. So it's a very unusual structure. What can we conclude from this structure? Well, the most basic thing, I think, is the tunability of the band gap in this semiconductor, which is quite unusual. And you can see the figure on the right shows the tunability of the optical emission, for example, from photoluminescence by varying the halide composition. So this is showing photoluminescence emission peaks. I've even color coded them for you to match the wavelength very broadly, right? So we have blue on the left, deep purple at 400 nanometers, and we have deep red heading into infrared up at 800 nanometers. And if you look at, it's slightly complicated, but you can see this left-hand arrow is the transition from pure chloride, X equals 3 on the left, to pure bromide, X equals 0 on the right, and that gets us up into green emission. And then we move from bromide, pure bromide on the second arrow, through to pure iodide, Y equals 0 on the right-hand arrow. And so, of course, the solar cell people want a short energy band gap, a long wavelength, so that they have maximum absorption of optical light. So you'd see the solar cell community tend to use the iodine-based perovskite halides. From a radiation point of view, we have quite different requirements. We probably want to maximize the band gap in order to minimize dark currents and minimize the conductivity of the material. So that's probably driving us away from the red into the green and possibly up to the blue. So in terms of lead halide perovskites for radiation detection, where typically most of the work has been done with bromine, which is emitting around 520, 550 nanometers. Now, the other thing that's interesting about perovskites is that they can be grown using quite simple methods. So this was a famous paper in 2016, which claimed nanocrystalline synthesis using a simple one-pot method. So again, if there are chemists amongst the audience, my apologies to you, because this is sort of one-pot chemistry for the non-expert, right? So you can essentially synthesize these materials by mixing and dropping them out of solution using the correct type of anti-solvents. So you really can make, for example, nanocrystals of organic lead halides using one-pot synthesis. So this was an interesting headline that caught people's attentions from IEEE Spectrum 2019. X-ray detection may be the perovskite's killer app. Perovskites are a wonder crystal that could yield images which are far more sensitive than commercial detectors. Well, that's unusual to get that sort of publicity in our area where technology develops very slowly. So what was behind this headline? Well, this was a nice review paper by the group in Bologna, published by Bazirico and co-workers in 2021. And this quite busy chart shows how the sensitivity of both perovskite and organic materials has developed over the years. So you can see the sensitivity to X-rays is given in these slightly unusual but rather standard units of microcoulombs per gray centimeter squared. And you can see that, for example, some of these early devices came along at roughly a sensitivity of about 1 in those units. And then things have really started to take off. And there are some highlights. So, for example, this one, 53, is a perovskite single crystal. And this was the first lead-free perovskite single crystal. Then we move to large area polycrystalline film. So 61 up here is a polycrystalline perovskite used for an X-ray imaging system, and you can see things continue to grow. And in fact, these sensitivity values start to get very large, up at 10 to the 5 microcoulombs per gray centimeter squared. And if we look into that in more detail, we find that actually there's gain mechanisms going on inside these materials to get such a high X-ray sensitivity. So let's look at perhaps the more familiar attenuation coefficient. So this is a plot on the left of linear attenuation coefficient for X-ray and gamma ray against some famous or well-known detector materials. And if we obviously have germanium and silicon. And if I remind you that the linear attenuation coefficient for gamma rays is principally driven by the Z number. So if Z of the material is low, the efficiency tends to be fairly low. And that's why silicon in gray is showing a linear attenuation coefficient quite a lot lower than all these other materials. And many of you will be familiar with CZT, shown in green, and cadmium telluride. And these are the sort of leading compound semiconductor materials which have a high linear attenuation coefficient for X-rays and gammas. But we've included on the graph the new perovskite material, Ma lead bromide, and you can see actually in several energy regions, it is pretty similar, if not slightly outperforming CZT. And of course, the reason for that is it's got lead in it. So lead is acting primarily, it's driving the high attenuation coefficient for X-rays and gamma rays due to the presence of lead. Again, those of you working in this area will be familiar with the so-called Klein plot. So the Klein plot shown on the right here shows the relationship between the band gap of the semiconducting material and the electron-hole pair creation energy. So shown in this plot as epsilon pair, the amount of energy required to create an electron-hole pair. This is a primary parameter of interest for radiation detectors, where we need to drift electrons and holes through a thick device under an applied electric field. And people postulated what the electron hole pair creation energy of a semiconductor might be. Is it twice the band gap? Is it once the band gap? It turns out it's a little bit more than twice. And this phenomenological expression of 14/5 times the band gap plus some offset energy is shown in blue. And things like silicon, germanium, CZT have fitted this line pretty well. Looks like first measurements indicate that the perovskite semiconductors are going to lie on that line as well. Although actually there's another branch shown in a dotted line here, which has traditionally taken some of the higher Z materials such as thallium bromide and mercuric iodide, and in this case cesium lead bromide was falling on this line. So it's a tricky measurement to make. You need a very well controlled high purity material to pin this number down, and I think it's fair to say it's a work still in progress. Okay, let's go on and talk about the growth of these materials. So one of the first papers that really first discussed the growth of large single crystal perovskites was by Seidmanov, Nature Communications 2015. And they presented a solution growth method to grow perovskite single crystals. Now, if you're used to high pressure, high temperature wafer growth, such as using Bridgman or Czochralski, this is a very different approach. And essentially, it's an extension of the method used perhaps by high school students. If you're, I don't know if we have any high school students present today, maybe you've done some crystal growth, traditionally copper sulfite crystals, on a string in solution. It's not that different. So if you look at this image sequence on the bottom, this is an image of the precursors, the materials required to grow the material, put into an anti-solvent and heated up. And you can see that after 15 minutes, a seed crystal has appeared at the bottom of the flask. And by well-controlled heating and well-controlled growth, this seed crystal grows very rapidly. And you can see by 3 hours, It's something which is several millimeters apart across. So what's going on here? This isn't kind of what we expect. And the key to this is to understand the solubility of the material. So here on the right is the solubility of the perovskite precursors in an organic solvent, which is dimethyl formamide, DMF. And we can see that as the temperature of the solution is increased, the solubility in this organic solvent actually drops. And this is counterintuitive, right? So we would expect normally solubility of materials in a suitable solvent increase with temperature. And here we have inverse solubility, where the solubility drops with temperature. So this gives us a nice mechanism to gently ramp up the temperature. And as the temperature goes up, solubility drops and the crystal precipitates out into the solution. And here's some examples. So here was another paper by a well-established group in Xi'an, Frank Liu's group at Shaanxi Normal University, published this paper in 2015, which showed very large perovskite single crystal growth. So for example, here's a selection going through chloride, bromide and iodide, reaching up to 2-inch diameter. And the other thing to note is these crystals have not been cut on a saw. So these are as grown, so they grow perfectly faceted. The left-hand crystal and the middle crystal are obviously cubic in their structure and are growing out in a cubic structure, whereas we have a more tetragonal structure for the iodide. And when you do the optical band edge absorption spectroscopy, you see the optical absorption showing the band edges increasing nicely from chlorine at around just above 400 nanometers, bromine at around 550, and the iodide at around 800 nanometers as expected. And this group was able to take this growth process and show some really nice results. Here's a sequence. In this case, it's Ma lead iodide, which tends to grow a little bit faster than the other two. And you can see this is a sequence A to B to C to D. And then left over 12 hours, the growth has continued to grow. And of course, the trick with this growth is optimizing the temperature ramping and the growth conditions to prevent spontaneous nucleation. You can see in picture A2, they're suffering a bit from spontaneous nucleation, where many crystals have started growing together. And that, of course, dilutes the growth away from one single site. Nevertheless, it's very nice, controlled growth. Other solution growth methods have been proposed. Here's just a couple I wanted to highlight. So several groups have tried a slightly different technique called anti-solvent vapor-assisted crystallization, where an anti-solvent is diffused through into the main growth vessel. Slightly unusual method, but it's produced some very nice, well-controlled crystal growth. A group recently reported aqueous growth. I mean, the headline claimed crystal growth in water, slightly disingenuous. I mean, it's crystal growth in acid, but it is aqueous based, and this was a first for these kind of crystal growth of perovskites. Normally, they're done in organic solvents, not in water. But we must also discuss the fact that solution-based growth is not the only method. And there is also an alternative approach, which is to use traditional high temperature, high pressure crystal growth for perovskite crystals. And one of the leading groups developing this method is Kanatsidis' group at Northwestern. So the group at Northwestern have pioneered Bridgman crystal growth as a high temperature, high pressure growth for cesium lead bromide. And this was some early data published from Northwestern showing a sketch here of the crystal growth. And if you're not familiar with Bridgman crystal growth, just to say it's completely different to solution growth. You put your precursors in a sealed glass ampule, and then you use temperature gradients with heating coils to liquefy and then cool and solidify out the crystal phase. It's a tricky method that needs a lot. It looks very simple. It's not simple in the slightest. And you need to understand your temperature gradients very carefully in your growth vessel in order to get a good result. You also need to purify your precursors very carefully before starting the growth process. And you can see some really nice crystals grown by the Northwestern group. This was pioneered by their colleagues Stumpos, who published early in 2013, has been developed by the group since. Now, I've alluded to the fact that this is not as easy as it looks, and that's certainly true. And one of the reasons it's not easy, particularly for the inorganic perovskite cesium lead bromide, so this is the inorganic lead halide with no organic molecule, which is really what you need for a high temperature growth. But the problem with cesium lead bromide is that this material undergoes phase transitions, specifically phase transitions during cooling. And you can see here I've highlighted the three main phases. Above 400 Kelvin, the material is cubic. Upon cooling, it goes tetragonal. And upon cooling below 360 Kelvin, it goes orthorhombic. And this causes problems because if this is not controlled very carefully, then the crystal will go through these phase transitions in an uncontrolled way during cooling. And this will cause either cracking or sort of slip planes and dislocations in the material. So this is quite an issue that needs to be controlled with this material. Let's go back to solution-based growth. So solution-based growth can be significantly improved by the use of seed crystals. I've already alluded to the fact that spontaneous nucleation is your enemy in solution growth. You don't want random nucleating sites. So often what's done is small crystals are grown first and then they're put back in to the precursor solution as a seed crystal. And you can see bottom left here a picture showing, in this case, Fa lead bromide, where there's a large seed crystal. This is 1 millimeter graph paper. So this is a sort of approximately 2 millimeters across seed crystal. And then it's been put back in and further growth has been achieved. Now, this can be a very effective method, but we have to be careful that the seed crystal doesn't introduce strain or stress into the larger crystal as it grows. And cross-polar microscopy is a very useful tool to look at stress in the material. So here's a nice example taken from this publication by Amari, who are the group in Leti in Grenoble. And they've done some nice work on Ma lead bromide. They've shown here regular optical transmission images. And you can see there's very nice material around the edges of this crystal. And there's something very strange and possibly rather horrible going on inside the middle. And if you switch from regular optical transmission to cross-polars, and you go over to the image on the right, you start the cross-polar imaging shows you strain fields inside the material. And the presence of bright light around the edges actually shows us that there's quite a lot of strain going on inside this particular example. So if we switch to a high quality crystal on the bottom right, here the situation is completely different. The optical transmission looks pretty good. There's no obvious features showing through the optical transmission. But when we go to cross polars, you see there is actually some stress at the seed point in the middle, but the majority of the material looks of very high quality. So it's a really useful screening method to show us the quality of the material. Now, I like to show this paper. This was a paper from 2021 by the group at Lausanne. They currently hold the world record, as it were, for growing the largest Ma lead halide crystal, and it reached 3.3 kilograms in weight. So this is an exercise, I think, for those of you out there struggling in your labs, this is an exercise in perseverance, right? You can see how they did this. So they grew many, many small crystals from seed using inverse temperature crystallization. They suspended them in larger growth chambers to grow larger volumes. And they kept going, right? These guys really persevered, and they grew many, many lead halide crystals. And they then fused them together using partial melting in the solution. And they built together a composite. And this really is the Rubik's Cube of Perovskite crystals. There it is. That's their record-winning 3.3 kilograms against the Rubik's Cube. Now, is it useful? I'm not sure. Is it a demonstrator of how far you can push the technology? Certainly, yes. Now, in fact, because of the many grain boundaries in this particular composite, they applied it as an X-ray dosimeter, gamma ray dosimetry, where you need a very large thickness of material. But I think it's a very interesting suggestion of where the technology could go. Okay, let's move on and talk about charge transport and electrical properties. Now, if you measure the charge transport in these materials, you often use time of flight. And if I remind you that time of flight is putting a pulsed laser often, or you can do it with alpha particles, but often with a pulsed short wavelength laser to create electron hole pairs just underneath a semi-transparent electrode. You watch them drift, and this gives us information about the electric field distribution and the mobility of the material. And these are the kind of pulses. Again, this is produced by Musienkos. This is the group in Prague, where they produce really nice current pulses. And you can see that this is the applied voltage: 6 volts, 8 volts, 10 volts, 12 volts. As the voltage on the detector goes up, the duration of this pulse shrinks, and the carriers are drifting faster. And if you analyze that drift time and you plot it in slightly different units, you essentially get drift velocity versus electric field. That gives you mobility, and they show very nicely the mobility of these materials. In this case, the whole mobility is better than the electron mobility and was just under 200 centimeters squared per volt second. And if you're used to working with CZT, if you're used to working with silicon, that's quite a low number. But actually, that's quite good for perovskites. And we've got to remember we're in a low mobility, long drift time regime with these materials. And look at the x-axis on my time current figure. These holes are drifting for tens of microseconds. This is extremely long effective lifetime of the carriers in the material. So although the mobility is low, the lifetime is very long. The group at Grenoble took this study a step further, and they looked at how they could extract information from these drifting current pulses and give information about the electric field distribution. And the data shows that as the current pulse drifts with time, the photocurrent magnitude actually gets bigger. That's not kind of what you expect, because the photocurrent is proportional to the drift velocity of the carriers. So why would it be increasing as you get towards the back of the detector? Well, the obvious explanation is the electric field's not uniform, and that they postulate that there is an increase in electric field as you get towards the cathode. Well, so that's quite a bold claim. So they went on to prove this with a very nice experiment where they put a slotted X-ray through a collimator and then moved it across the side of a detector. Very tricky measurement to do. If you go to a synchrotron with a microbeam, that would be an easier way to do it. But this was a very nice measurement in the lab. And it showed differences in the sensitivity or the photocurrent that's produced, which varied from one side to the other, or when they switched the polarity, it varied from the second side back to the first. And it was direct proof that there's a variation in electric field inside these devices. And this is something we need to understand better. Now, I've already alluded to the fact that the lifetime of the carriers in these materials is surprisingly large. And in fact, their photoluminescence brightness is surprisingly high at room temperature. And photoluminescence can be used in a time-resolved mode to measure the carrier lifetimes in these materials. I won't go into the details of this paper, but nevertheless, it gives a hint that the carrier lifetime can be microseconds. Now, it's quite tricky to do it with photoluminescence. There's a much more reliable method is to do it in microwave. So this is a paper on the right which reported microwave-based carrier lifetime measurements in single crystals. And this showed lifetimes of up to 15 microseconds. So this is really corroborating the data we see from the direct measurements earlier. So let's move on and look at gamma spectroscopy performance, because this is really where we want to get to. This is one of the application areas for perovskite detectors. So at the moment, the best gamma spectroscopy is being reported from perovskite crystals that have been grown by Bridgman methods. And so again, this has been pioneered with cesium lead bromide, published by the Northwestern group. And this work's been done in collaboration with colleagues at Michigan. So Zong Hei's group at Michigan are also working on these systems. And so here's some data I'm showing you here from some of their publications. This was early alpha particle response from cesium lead bromide, a broad peak, but nevertheless nicely resolved, moving with applied bias in the way you expect. First evidence of a rectifying contact, suppressing the leakage current at reverse bias, which is sort of what we need. And here, both holes and electrons with a Hecht plot. So this is the standard method where you measure how the centroid of the alpha particle peak is shifting with voltage. So this acronym CCE, charge collection efficiency, is essentially the normalized position of this alpha centroid. So it's shifting down it's shifting up with voltage as the electric fields become stronger, and you can see asymptotically these figures go up. When you do the analysis, you get the mobility lifetime product, the Newtown product, and both these materials were coming in at mid to high 10 to the minus 4 centimeters squared per volt, which is pretty respectable for a new detector material. So gamma spectroscopy has been reported from cesium lead bromide with some quite nice results. So again, this is from the Northwestern Michigan collaboration. And you can see a figure on the left, cobalt 57. So this is a well-known gamma emitter at 122 kV, and you get quite a well-resolved peak. But notice, as a result of using high Z materials, you can't avoid the escape peak. In this case, the escape peak of lead, which is showing at about 80 kV down from the main photo peak. And that's just the K edge of lead. You can't avoid it. It's always going to be there. If we move to cesium-137, which is a much higher energy gamma source, here's the photo peak at 662 kV, and here's the lead escape peak, again about 80 kV down, showing at about 580. And again, this was quite a small piece of cesium lead bromide, so it's quite a lot of scatter with a Compton edge. So again, first results have been shown of cesium lead bromide processed into pixelated detectors. And I won't go through all this, but you can see here there's some simple structures with 4 pixels in an array on top of, in a single crystal, producing some rather nice energy spectra. If you move from a planar detector to a pixelated detector, several things happen. Generally, to improve your spectroscopy, the so-called small pixel effect tends to minimize charge trapping and is generally beneficial. So you can see that the gamma spectrum is showing nice resolution, just under 2% with the large lead escape peak. And this was more recent results, which are now published by Michigan and Northwestern, showing resolution below 2% for 137 cesium gamma spectra. Now, the interesting thing is you can estimate from this data the carrier lifetimes that must have been in the material to produce these spectra. And this data is consistent with whole lifetimes in excess of 100 microseconds, which is quite astonishing. Lifetime mobility is quite low, but the lifetimes are extremely long. And just on the topic of, when we think about gamma spectroscopy, we need to think about the stability of these materials. Various tests have been reported over the years. This is a paper that showed the dark current, well, the photocurrent stability of an Ma lead bromide single crystal irradiated with 200 gigabecquerels. So this is a huge activity, a huge dose that's been put on this material over 100 hours without any really disastrous effects. In fact, perovskites appear to demonstrate what's referred to as self-healing. So damage, radiation damage or thermal damage, however it's occurred, which can tend to break down the perovskite into its constituent atoms, can be reversed and brought, and the damage can essentially anneal out or self-heal out at room temperature. There's quite a nice demonstration of this shown by this figure. So this was a sketch that showed the mechanical synthesis of Ma lead bromide by mechanical milling. So you can see what happened is you start with your precursors, so lead bromide, a white powder, methyl ammonium bromide, a white powder, and they were simply put into a pestle and mortar and they were stirred. And you can see that with each iteration of the stirring, there's a spontaneous room temperature reaction, materials going from white to orange, and finally, with enough agitation, a full synthesis of the orange material, which is Ma lead bromide, is produced. And of course, in reality, you can do this in an automated way with a ball miller, and you can show direct chemical synthesis by sort of energetic mechanical mixing. There are other particular peculiarities of perovskites we need to be aware of. There is the mechanism of ion migration. I think I'm going to skip the details of this given the time, but just to be aware that ions migrate, there is ionic conductivity in these materials, and we have to take what steps we can to reduce it. Okay, so let's move on to X-rays. So as well as gamma spectroscopy, we want to develop perovskites for X-ray imaging, as I said at the beginning. So this is one of the first reports of a perovskite-based X-ray imager. It's a polycrystalline material now. You can see a cross-section through the active perovskite layer, which is made up of many polycrystalline phases, crystallites jumbled together, fused together. It turns out that this material is extremely tolerant to the grain boundaries and the defects introduced in polycrystalline material. And this report by a group from South Korea produced some really nice, fairly high quality X-ray images using this polycrystalline Ma lead iodide. Other similar reports have been shown. So this was an amazing report of polycrystalline Ma lead iodide wafers that were pressed out to 8 centimeters. So this is a thing, this is a disc the size of a large donut, this thing, and produced really high sensitivity X-ray imaging devices. So this is a technology which, if you can cope with the polycrystalline nature of the material by various mechanical methods, you can synthesize really large areas. So we've got away from the constraints of single crystal material, and now it's got much bigger. And you can see this is data for another variant of one of these devices, where you can see the X-rays are turned off, on, the X-rays are turned off, the X-rays are turned on at a higher dose and off, on at a higher dose and off. And you can see the step increasing each time. So here we're measuring the linearity of the response to X-rays and also the on-off ratio, the very low dark current in this particular example. So I wanted to finish on scintillators because I said at the beginning of my talk that perovskites are an interesting material because not only can we use them for direct detection, we can also use them as scintillators. And one way of doing this is the so-called nanocomposite scintillator. And in a nanocomposite scintillator, we're introducing nanoparticles into either a scintillating plastic or a passive plastic matrix. This was a very impressive report by a group in California that showed nanocomposite scintillators working with extremely high percentage loading, in this case of quantum dots. These weren't actually perovskites, they were cadmium selenide based quantum dots. But you can see they managed to introduce up to 68%, which produced very high scintillating plastic scintillator. So let's see if we can, why would you want to do that? Is the obvious question. Well, the obvious reason is you want to introduce high Z material into a plastic scintillator, because then you can increase the efficiency and also get some energy absorbing properties. And here's an X-ray simulation showing how the photo peak efficiency of a 1 centimeter piece of plastic scintillator can improve if you add relatively small amounts of high Z perovskite nanoparticles in. So you can see in gray, this is the plastic only, showing that the efficiency drops off very quickly. This is 10 kV, this is 100 kV, 1 centimeter thick. So if it's only plastic, the efficiency drops quickly. But as soon as you add, let's say 10%, 11% of perovskite with some lead in it, you start to get the yellow figure here, where you get the absorption edge from lead, really pushing the photo peak efficiency up. And you can simulate the effect of this, of adding high Z nanoparticles into plastic. And the top one is showing the simulation for americium-241 gammas at 59 kV. And the bottom one is showing the similar simulation for 122 kV cobalt-57. And again, the photo peak that is missing when it's purely plastic grows quite strongly with relatively low loading of high Z material. So can this make a realistic scintillator? Well, the first steps are heading in the right direction. This is work done at Surrey, where we have been looking at nanoparticle scintillators based from formaldinium, lead halide, and you can see that we've synthesized the lead bromide, the lead chloride, and a whole mixture in between, and you see the emission wavelength shifting from green to blue. Perovskite nanoparticles have been recorded with light outputs in close to, if not in excess of, traditional inorganic scintillators. This is a really nice paper from a few years ago in Nature, which looked at cesium lead bromide quantum dots. If they had a normalized light yield of 100, they were getting quite close to a similar thickness of cesium iodide scintillator. The proposed model for X-ray scintillation in nanoparticles, well, it's fairly similar to photoluminescence, for example. In this case, the incident X-ray ejects a high energy electron by photoelectric ionization, and the secondary electrons are very energetic, and we require them to thermalize through the production of excitons to then produce fast radiative recombination to produce scintillation light. And first studies have shown that this is the photoluminescence, for example, follows the expected trend. Photoluminescence from cesium, Fa, and lead bromide and cesium lead iodide. The photoluminescence decay time. Actually, in this case, this was X-ray radioluminescence using a pulsed X-ray source, showing long decay times, which indicates long-lived excitons within the material. And a practical first demonstration of perovskite imaging detectors. This was perovskite scintillator put on top of a standard amorphous silicon TFT sensor panel. So this is a Perovskite X-ray imager, but working in scintillation mode rather than in direct detection mode. Other reports have shown Perovskite loaded nanocrystal in glass, which again have shown some really nice bright luminescence as a function of loading. And I just wanted to finish with this one on the scintillators, because there is a whole new class of perovskites beyond the scope of this talk. I've really been talking about the lead halide perovskites, but there's other classes of perovskites, such as the so-called lead-free double perovskites. And some of these have great promise as scintillators because they have very high Stokes shift. And the Stokes shift is the difference in wavelength between the emission edge and the absorption edge. So on the left here, this is a rubidium-based lead-free perovskite, which has an absorption edge in the near UV at 266 nanometers, but it emits its scintillating light at 480 nanometers. This is extremely bright scintillator, and you can see some measurements being made where it was used to detect 511 keV annihilation photons from sodium-22. So I think that's a good place to come to an end. Hopefully I've given you an overview of perovskites, some of the opportunities and achievements over the last 5 years. I've discussed a range of the different synthesis methods, including both low-cost solution growth and also more traditional Bridgman high-temperature growth. I've given you a quick overview of the electrical and optical properties and how they've been demonstrated first results as radiation detectors, both as direct detectors and scintillators. So I'd like to thank you for your attention. I hope that's come over to you all right online. And I would like to, of course, advertise on the next conference that will be covering this. So maybe you'll be able to make it to the IEEE meeting, which is in Milan in Italy in November. And there'll be several dedicated perovskite sessions in the RTSD symposium as part of that meeting. So I'd like to finish at that point. Thanks very much.
Thanks, Paul. Very, very interesting lecture. And I'm looking forward to going to Milan in November. So hopefully I'll see you there.
I hope we'll be there in person.
Yeah, that's the hope. There are a few questions in the chat. So why don't we start with one about the crystal growth method, particularly the solution growth method. And there's a question about how the crystal is able to maintain its uniform shape during that process.
Yeah, okay, that's a very good question. Let me try and flick back and we'll get back to a few pictures. But yeah, as the thanks for whoever asked that question. As you can tell, the ones which are shown tend to be very rather carefully selected. I mean, certainly in our lab, you have to battle two problems here. One is spontaneous nucleation, as shown here, where suddenly the solution crystallizes in many different points. And then the other one is irregular growth. Now, actually, these things grow amazingly faceted. You know, they really, sometimes you get two seed crystals stuck together, and that will obviously give you an irregular growth. But there is an art to controlling it. It requires good understanding of the concentration of the precursors. It requires very careful temperature control. And there's a few other magic tricks that people tend not to talk about in public, which is all part of the mix, you know, to get these things to work rather well.
Great. Along similar lines about the growth and the machining. So how well can these crystals be machined? Are they brittle? Can you cut them? Like, how do you shape them into?
Yeah, well, that's a really interesting
crystal
one.
To a detector, right? How do you machine them?
Well, so it's a whole new world, right? So we do not have a mature technology for processing and contacting these devices, these crystals into devices. The perovskite crystal is very soft, so it's very challenging to polish it. So people have developed bespoke polishing regimes which are designed specifically for soft perovskite material, and it's not at all easy. So if you're used to CZT, where you could get your alumina powder out and put it on a lapping machine and it, you know, put the thing in wax and off it would go. This is different. So that is tricky. And the whole aspect of semiconductor perovskite contacts is also very early days. And I mean, you can look at the work functions of the metals and the semiconductor. You can predict what metal Schottky will make a good high barrier contact, which should give you a rectifying contact, which is what you want. You can make the contact to the best of your ability, and it does not correlate with the expected barrier heights at all. So it's a very unclear at the moment area. So I think there's a lot of work needs to be done to improve contact quality.
Yeah. Are there any challenges with the fact that so many of the compounds contain lead, just being, you know, heavy metal, hazardous materials, handling type precautions, or is it pretty much okay?
It hasn't caused us any problems. I mean, I think from a consumer end application point of view, it may cause an issue down the line, but certainly that's not where the toxicity, if there is any, lies. You know, handling the organic solvents. Some of these grow in GBL, and GBL is a solvent that's being restricted, certainly in Europe, because of its use by people growing drugs. So there's things like that which are quite tricky. Getting hold of some of these organic solvents is difficult, but clearly to go lead free would be an attraction, and I say there are these other classes of materials coming along which don't have lead in them, which might be an advantage.
Great. There's a multi-part question about, I'm just going to try and summarize, about the possibility of using these perovskite based materials to detect neutrons.
Yeah.
So
okay,
can you just speak broadly about that?
Yeah, so, well, it depends whether you mean thermal or fast. I don't know if the question specifies.
It doesn't talk about both.
If it's thermal, it's quite tricky. You obviously need some isotopes in there with a high cross section of thermal neutrons. Some of the lead-free materials do have some atoms in there which have a reasonable cross section, but they are not very mature yet, I would say. The fast neutron detection is, I think, more interesting because of the organic molecule. So if you go for an organic perovskite, then obviously you've got a lot of hydrogen in there, and then you'll get proton recoils from a fast neutron. And so that is certainly an area of active study. People are looking at their sensitivity to fast neutrons from the proton recoil of the organic molecule.
How is the light coupling, or how is the response coupling from that proton recoil? It's not a scintillator. Is it actually scintillation light, or how do you get the signal from that proton recoil?
Well, if you could go either way. So in a charged particle, if your fast neutron gives you a proton recoil inside the material, you'll pick that up as a charge signal. Or if you have it as a scintillator, you would get it through the scintillation. I guess it's no different to you know, fast neutrons in GAG or in cesium iodide. Well, no, that's not a good example, is it? Fast neutrons in a plastic where you've got a proton recoil there.
That's right. That's what I was kind of thinking, because that's my area, and we're often, you know, the higher the collision nucleus, the kind of less energy gets transferred, and that affects the light. But if it's a direct charge signal, then that's obviously a little bit different. So the last question actually I'm going to ask, and it was about the modeling. So you showed some Jan4 results. So can you talk a little bit about that model, and are you modeling the actual, how much detail is in that, right? Is it the tracking all the recoil nuclei, or how does it, what details are in there? Looks like perhaps Paul froze.
Frozen and dying.
Can anyone else hear me?
Yeah, we hear you.
Okay, perfect. Well, at that point, maybe we'll just chalk it up to an internet failure on Paul's side. Thank you all for your attention today and coming. You can find the lecture online if you joined late. There's a link in the chat where you can find all lectures or all recordings of this lecture and all previous. So thank you all for your attendance today, and we'll see you on, I believe, Tuesday for next week's summer school. Thank you.